Well, thank you all for coming, and thank you for remaining for the last session of the day today. Before I actually introduce my esteemed colleague from Databricks, my name is Jules Damji, and I'm the Spark Community Evangelist and Developer Advocate for Databricks. And on behalf of Databricks, I do want to thank Capital One and Yuri in particular. Give them a big hand, please. This is our second Spark Saturday since last year. Normally there is this misnomer about sequels are terrible, but I think this was the best sequel I've seen happen two in a row. So it was brilliant execution. Again, thanks for Yuri's team, and also I want to thank my counterpart, Donna from MetaStream, who actually did a brilliant job in executing all that. So give them a big hand. Now, our last speaker today is from Databricks, my esteemed colleague, Silvio Fiorito. He is a resident architect at Databricks, and what does that mean? It actually means that he actually lives and breathes customers' problems in deploying Apache Spark, including Capital One, who actually played a significant role. And over the years that he actually has worked as a resident architect, he has sort of garnered a lot of very secret knowledge that he's going to share with you about what are some of the lessons that people normally stumble into, and what are the lessons that he can actually share with you. And so please give a big hand to welcome Silvio Fiorito from Databricks.
All right, thanks everyone for sticking it out to the last session of the day. I know there's cake after this too, so that's a good reason to stick around. My name is Silvio Fiorito. I'm a resident solutions architect with Databricks. Just real quick, I think by now everyone knows who Databricks is, but Databricks was founded by the original creators of Apache Spark. The mission of Databricks is to make big data simple, and we do that through our managed service called Databricks that we provide to customers in the cloud to simplify and optimize running your Spark jobs. All right, a little bit about myself. As Jules said, I'm a resident solutions architect. I am local here, based out of Herndon. I have been a developer, Spark developer, consultant, trainer for a number of years, going back to basically Spark 0.6 around that time frame. I actually got into Spark because at the time I was doing a lot of work around application security, forensics, cybersecurity. So you can imagine that's a lot of data volume, a lot of insights that you're trying to get out of the data, and you're wanting to do that very quickly. So at the time, everyone was going towards Hadoop. I realized that really wasn't what fit what I was trying to do, and I found this small project out of UC Berkeley called Spark. It was very rough around the edges at that point. A lot of the APIs that people use nowadays weren't even designed at that point. But I've been using it since, and I love it, and absolutely love working at Databricks, where I get to use Spark every day. As I mentioned, I am local. I'm a GMU graduate, and also had a detour where I spent some time in the Marine Corps prior to coming to Databricks. So what I wanted to talk about today, I kind of broke it up in three sections. I work with a lot of different customers, Databricks customers, and even prior to Databricks, a lot of different customers working with Spark. And I tend to find a lot of common themes in the questions and problems that they're running into. So I wanted to kind of distill it down. It's an area that you could spend a week covering. So I wanted to cover three main things. One is speeding up file loading and partition discovery. Two, optimizing file storage and layout. And then the third one, which is more of a nebulous area, which is simply faster query times. Right? And that can, again, involve all sorts of different areas within Spark. But I'm going to cover some that I've found useful. So first, one question that I tend to get a lot is, why is it taking so long to load my data frame? And I put load in quotes because if you're familiar with Spark, and if you're new to Spark, hopefully you attended Jules' training, you should know that Spark is lazily executed, right? So you're not actually loading any data, right? When you define a data frame or an RDD, you're pointing to some location in your storage system, and then Spark really isn't going to do anything until you finally give it an action to perform. And an action would be, displaying the data, counting the data, writing the data out. So this code right here, right, I'm using the DataFrame API. I'm saying spark.read.load. I have some data set. In this case, I'm running in Databricks, so it's some data set on S3. Then I immediately apply a filter. Presumably, this is going to be a partition filter on the data set. And there's no action here, right? I haven't done any action. So why are there jobs running? And if you notice, it took almost 45 seconds to run this command. And I tend to get this question a lot. And with customers that have extremely large data lakes that are on S3, they tend to run into this problem very often, where they're pointing to a data set, they think they've done everything that they're supposed to do, they partition the data set, and then they go and want to run some query, or maybe they're running some ETL job, and the first thing they do, it just sits there for seconds to minutes waiting with nothing happening. So first, some background, and I have to warn you, I am going to do a bit of a deep dive here. So if you're new to Spark, just file this away, and it'll be useful later on. If you've been using Spark for a while, hopefully this will be helpful to you. So some background. When you use the spark.read .load command, that internally is using what's called the data source API. So Spark has some built-in file formats that it supports via the data source API out of the box. So Parquet, CSV, ORC, JSON, et cetera. But this is also how third-party extensions get loaded. So if you have like Cassandra or Avro, which is not baked into Spark, but it's a Spark package. So in this case, I'm going to be talking specifically about file formats. So these are file formats that you're loading from HDFS or S3. So the first thing Spark has to do is actually, for data frames, is get the schema for the data that you're loading. Now, in order to get the schema, it needs to read the files, understand the layout of the file system that you're pointing to. And in formats like Parquet or ORC, the schema is actually baked into the file format. So in order to get the schema, it actually has to start reading some files. In order to read the files, it needs to actually do a file listing. And if your data set is partitioned, it has to actually do partition discovery. So how does it do that? So internally, Spark uses what's called an in-memory file index. This is responsible for, like the name describes, indexing the files that you're planning to load. Now, it does the partition discovery. So if you're not familiar with partitioning with data sets in the Hadoop world, these are Hive-style partitions, right? So you have a data set, and it's always a good practice, especially for like analytical queries or time series data. You essentially partition or lay out the files based on some date or timestamp, something that you're going to typically be filtering on, right? And this lets you reduce the amount of data that you have to read in when you're doing common filtering on your data set. So in this case, it's partitioned by a date field. So the way it works is Spark will first do a file listing on the base path that you defined. What it does is it sees how many base paths there are, right? So if there's any, how many directories there are. Now, there's an internal parameter called the parallel partition discovery threshold. It defaults to 32. So anything above 32 partition directories, Spark is actually going to kick off a job in order to get all the file listings in parallel. In addition, if you have deeply nested partitions on your data set, Spark also has to discover those nested partitions. So all those things are actually quite expensive, especially if you're on S3. So file metadata and file listings on S3 do take some time. So that's why it's parallelized. Now, once it captures all those file listings, obviously you want to minimize the times you redo that. So actually, Spark then also uses what's called a file status cache internally. And that also has a parameter that I have linked here, but the default is 250 megs. And that 250 megs is shared across your Spark application. So it's something to keep in mind. If you have multiple users sharing a Spark context, they're all going to be sharing this 250 meg cache. It is something that you can tweak if you need to. Now, once Spark does this partition discovery and file listing, it's going to map these partitions into basically columns for your data set so that when you apply a partition filter, it can then figure out the exact files it needs to load, okay? And this is one important thing to keep in mind here is that these are using the same data types and data structures as data frames. So that means that when you're doing these sort of partition filters, you can use all the complex functions that are available to Spark. So if you're, if you have a time series data set, you want to do like relative time ranges on your partitions, you can absolutely do that, and Spark is smart enough to apply those functions and only pull out the partitions that you need. Okay, so going back to the example, what happened here? So in this case, I have 1,823 partition paths under this data set, under this path. So even though I'm filtering, if you notice I'm filtering after I called spark.read.load, I'm filtering by 4 values specifically, but Spark, the way Spark works with the file formats is that it's going to index all 1,823 partitions. So again, not very efficient, right? So if I only care about 4 dates, why am I having to get a file listing on almost 2,000 partitions? So you can see here when I do the actual explain plan, so if I were to actually execute the query, you can see here and highlighted, it's actually going to just load. You can see here there's the partition count 4, so it's only going to load those 4 partitions. And here partition filters is how I can validate that it is applying my the expected partitioning. So how do you deal if you've got a case where you have thousands, hundreds of thousands of partitions, and you don't want to basically suffer from this delay, especially if you're doing interactive type queries. So one option is if you know exactly the queries that you want to load, you know the partition layout, meaning you know how the folder names are structured and so forth, and you absolutely want to stick with files, right? You don't want to use data source tables. You want to use the file formats directly. There's an option called base path. So you specify the base path of your data set, and then in the load command, you specify the specific partitions that you're interested in loading. When you do that, Spark is smart enough, the in-memory file index is smart enough to say, okay, they gave me a base path. From that base path, infer the partitions that they've told me to load. So when we do that, this is what the code looks like. And you can see I still specify the base path here, and then these are the partition paths that I specified. And it goes down from 43 seconds to 2 seconds. And keep in mind, this is not a large data set that I'm using here. This was maybe like 1 or 2 gigs. It was on a small cluster. But again, keep in mind, if you're working with like a multi-terabyte data lake, this is probably something that you want to keep in mind and you may have hit already. Now, another option, starting with Spark 2.1 and later, is using data source tables. So the way data source tables work is that the partitions are actually managed within the Hive metastore. Now, Spark, if you're using Spark on your Hadoop distribution, you can connect Spark to your Hive metastore. If you're on Databricks, we have a built-in Hive metastore out of the box that is automatically available to all clusters. And whenever you save a data set using the Save as Table API, and I'll show a couple different ways you can do that, all the partitions are going to get managed in the Hive metastore. And we've specifically made some enhancements to the metastore and the catalog, the Spark catalog in 2.1 and later, to handle thousands, hundreds of thousands of partitions. So there's actually a blog post by Databricks earlier this year specifically on this use case. And it's called Scalable Partition Handling for Cloud Native Architecture. Okay? Now, the cool thing here is that, one, it doesn't have to do any of this partition discovery. It doesn't have to do any of these file listings. And it still is smart enough to apply the partition pruning at the Catalyst logical planning stage. So you get all the advantages of partition pruning without the expense of having to do this discovery at startup. So this is what it looks like. So in this case, if you notice, the API's changed slightly. So I'm using spark.read.table. I'm specifying the table name, which I previously saved in the Hive Metastore. I'm still applying the filter. And if you notice, it went down now to less than a second. Okay? So again, if you're doing interactive type of workloads, this is definitely something that you want to consider. But even batch jobs, right? Think about a batch job where you're maybe using the first API I showed, right? Again, you have terabyte, multi-terabyte data lake, and maybe you're doing some sort of ETLing or aggregations, processing. It's, again, something that can help speed up your jobs and just make them more reliable. So how do you use the Spark's data source tables? So one option is to use what we call external or unmanaged tables. So this is where you define a Metastore table over an existing data set. So you've saved this data set on S3 or HDFS, and now you want to use the Metastore for the partition handling, for the schema management. Maybe you have SQL users that they don't know Scala, they don't know Python, they don't know what format they should be using to load the data, where to find it. Right? That's the point of the Metastore, right? To abstract the underlying storage format. So when you do this, when you create this unmanaged table, it's going to run the partition discovery once. And then as you add additional data, you can use the save as table or insert into APIs. And when you do that, it's going to add those partitions to the Metastore. Now, the other option is to actually create a managed table. Now, the reason we call it managed and unmanaged is because with unmanaged tables, you are responsible for managing the underlying files. That means if you drop an unmanaged table, it's not going to touch the data that you wrote out in S3 or HDFS. With a managed table like this, I first create the table, I give it the schema, I give it the file format that I want to use, in this case Parquet. I tell it how to partition the data set, and then going forward, I always have to use the save as table or insert into APIs to add data. Now, if I were to drop this table, it's going to delete any of the files that I created previously. Okay? So it's an important distinction to keep in mind as you're using these APIs. So if you're wanting to use create tables via the DataFrame API, this is how you would do it. So the top one being a managed table, so you just give it, dataframe.write, partition by, and then save as table. If you want to do an unmanaged table, you specify an option to the path that you want to write the data to. Okay? Now, if you have some process with an unmanaged table that adds partitions to that, you can do that, but then you have to go back and make sure you explicitly add the partitions, because at that point, the Metastore is not going to know about the data that you added externally from the Metastore. So one way you can do that is with this API here, or this command here at the bottom. It does a repair table, and it basically goes and rediscovers all the partitions under that path. So just to recap, so data source tables versus files. So again, tables, more scalable partition handling. Schema is managed in the Metastore. You typically will have faster job startup, whether it's interactive or batch jobs. Also, one thing that I'm going to cover later is you'll start noticing a theme that because we're using a Metastore, we can add additional metadata to the data set. So we can add statistics that are used in the CostBased Optimizer that I'll cover later, and just additional things that we can do with Metastore tables that you can't do if it was just files sitting on HDFS or S3. And with tables, you can use both SQL and the DataFrame API. So you're not limited to just SQL, right? The Hive Metastore is just keeping the metadata, but you can still use both APIs with it. With files, like I mentioned earlier, partition discovery, it's going to happen every time you define a data frame. So if I go back to that original example and I run that cell again, it's going to do the same thing all over again, right? it has to infer the schema at data frame creation time, right? Each time. Again, if I redefine that data frame, or if I create a different data frame over that same file path, it's going to do the same thing again. Like I mentioned, you're typically going to have slower job startup time. And the only statistics that you're going to get is basically file size, because that's all it gets from the HDFS or S3 file listing. And of course, you can only use them with the DataFrame API unless you create a view, DataFrame view over that, and then you can expose that to SQL. So again, if you have like SQL users, you're better off absolutely using data source tables. So one other thing that I wanted to cover is schema inference with CSV and JSON files. Now with Parquet and Orc, the schema is baked into the files, right? So that's easy. Once it gets a file listing, it can start reading the schema, the column names, column data types, and so forth. With CSV and JSON, these are just text files, okay? So what Spark has to do is actually, well, an option, if you don't have the schema, what it actually can do is do schema inferring on the data set. But the way it does this is it has to actually run through the whole data set, okay? So it's convenient, but extremely slow. So again, I've had some customers that, they have hundreds of gigs or, terabytes of CSV files. They know that Spark supports CSV out of the box. I have this great option where I say infer schema true, and it automatically gives me my schema and data types. It's so great. And I'm just going to point it at my hundreds of gigs of CSV files, and it's just sitting there for minutes, hours, who knows, depending on how big your data set is. So it will definitely be a lot slower. And it can get even worse if you start dealing with Gzip compression, which is not splittable, right? So if you have, 5 files that are Gzip compressed, you could have the biggest cluster in the world. It doesn't matter. You're going to have 5 threads that are going to go over each of those files. Another issue that can happen is if you have, a lot of small files on HDFS or S3, and so again, there you're going to hit a penalty of just doing all those file listings and iterating all of through those files. So what are some options? One, obviously avoid schema inference unless you absolutely need to. If you need to, and if you know that your data is consistent, what you can do is instead of doing it across the whole data set, just pick one file, right? You don't have to, if you know that all your files have the same consistent schema, you don't need to scan a whole terabyte worth of CSV files. Just pick one file, use that, save the schema, and then apply it over the rest of the data set. You can save that later on. So the Spark schema data structure has a convenient function that lets you save that out to JSON, and then you can load it back in. And I'll show an example shortly. If you're doing this with JSON, what you can also do is you can actually tell it to sample a subset of the data. So there's an option called sampling ratio. It defaults to 1. You can reduce that, and then it'll just do a sample of the data set. So here I have, again, a data set. In this case, this is a different one. This is actually CSV. It's not partitioned. So this time here is actually not for partition discovery. It's in a flat structure. So it spent almost a minute trying to do schema inference on this CSV data set, okay? So one option, like I mentioned, just pick one file out of the whole data set. So that took me down from 48 seconds down to 6 seconds, okay? So again, because I know that this is a clean data set, I know that the schema is clean, I can trust the schema from one file will apply to the whole data set, I can use this trick here. Now another option would be to load the schema once, save it as JSON, and in this case I have a JSON string here, and I'm using one of Spark's data types structures to load from JSON, and it turns that into a schema. And then I simply say load CSV using this schema. And that went even further down to less than a second, okay? Because it has to do no scanning of the data. So if you notice, there's no jobs at all here, right? It just, it's going to apply it as it runs. All right, next question I tend to get a lot. What format, compression, partitioning scheme, et cetera, should I use for my data set? So if you've worked with Spark, you know that Spark really tends to excel with Parquet, right? And especially for analytical queries, where you're maybe working on a subset of columns, you're doing a lot of filtering and aggregations and so forth. You really want to stick to columnar file formats instead of text. So with Parquet, you get column pruning and predicate pushdown. So what does this mean? If I have a data set with 1,000 columns, I have Parquet files with 1,000 columns, I'm doing aggregations and filtering, and it turns out I'm only using maybe 5 of the columns out of that data set. Spark is smart enough to know to only load those particular columns from the data set. So why does that matter? One, you're loading less data, especially if you're working in cloud environment from S3. That's going to reduce the amount of data transfer coming from S3 to your cluster. Two, it's just, in general, less data that you're bringing into your executors, right? And Parquet also has a lot of good statistics and metadata within it that helps Spark optimize the queries, and in some cases can even help us skip certain rows and drill down specifically to certain files that have the data that we're interested in. Now, CSV and JSON, again, they're text, right? So when you load like a CSV file, you have to give it a delimiter. And as it loads the data set, it has to parse each row by that delimiter. It has to extract each of the columns. And it has to map each of those columns to the data type in your schema. All right? So again, you could have 1,000 columns in the CSV data set, but you're only using 1 or 2. It doesn't matter. It has to parse each line and go through each line and each column and map that. And then finally, after it's parsed that, then it's going to do the column pruning after it's read all that data. Okay? And of course, it doesn't have any sort of predicate push down or filtering. The most that you can do is do partition filtering. So in terms of compression, you do want to tend to stick to splittable compression formats. Again, obviously Spark is a distributed framework, so you want to be able to split your data sets across your executors. So you can do that best with splittable formats. Now, if you're using Parquet, because of the way Parquet stores data, you can use non-splittable compression formats like Gzip and Snappy, because you're not compressing the whole file, you're compressing the blocks within this Parquet file. In fact, in Spark 2.2 and later, the default is now Parquet and Snappy when you save data. So it used to be Parquet and Gzip. Snappy has just better performance compared to Gzip, so that's why they made that change. Now, what you want to avoid absolutely is large Gzip text files, like CSV files. Again, Gzip is not splittable, right? So if you have a 10 gig CSV file, you're going to load it with a single thread. And I have seen this. I won't name names. With some projects, someone says, oh, I'm having problems loading this 120 gig Gzip CSV file. Well, it's going to be slow. I can't do anything about that because you can create a 1,000-node cluster. It doesn't matter. You're only working with one thread. Also, one issue that tends to crop up when you have these very wide text. Sorry? Ideally, if you can go upstream and tell the data owner, like, hey, what are you doing? Use some common sense. Most likely they're not someone that works in the Hadoop ecosystem, so they probably didn't even realize what they were doing. So ideally, you would just go further upstream.
Sometimes splitting a file may not be an option because of the data.
Well, so are you talking about like multi-line files?
I got a mic here.
Yeah. Actually, could we cover that after? Just because I'm already running low on time, I want to make sure I don't. So yeah, well, we can cover that. There's a few different ways. So yeah, so real quickly, the other thing with text files, especially these really wide tables and CSV files, is that you can hit garbage collection issues with Java, okay? With the Java garbage collector, right? Again, because what's happening is, as it's reading all these columns, it's creating a big array, and it's creating all these objects as it's reading the files. So you're having garbage collection issues. Now, there's a good session by my colleague Vida Ha and Cheng Lian from Spark Summit, San Francisco, that I've linked to here. They go into a lot more details on file formats and compression, and also give some examples that they've seen in the field. So definitely recommend to see that. Now, partitioning, I covered partitioning a little bit, but just to recap, partitioning gives you coarse-grained filtering of input files, right, based on directory structures. The one thing you want to be aware of is you want to avoid over-partitioning, right? So if you have like a date field in your data set, if you partition by that date field and you find files in those partitions that are very small in like the single-digit meg or even less than that, that you're probably over-partitioning, and you want to partition further up, maybe at the month level or year level or some other field. Because what you want to avoid, again, is dealing with all these small files as you're processing in Spark. Bucketing is another option which writes your data out already hash partitioned. So this is good for when you're doing a lot of joins or aggregations on certain fields in your data set. So think about like lookup tables, right? So if you have like a large data set, kind of like a star schema type of data warehouse, and you're doing a lot of joins or aggregations on certain fields, you can bucket your data by that field, and when Spark reads it in, it knows that the data is already hash partitioned by that field. So if you do any sort of shuffle operation, it's not actually going to shuffle the data around. So that's a huge time saver in terms of optimization. Now, the one thing is that it does need to be a data source table, again, because we're saving the metadata of the bucketing in the Hive metastore. And so this is what it looks like in the API if you were to do that in this case in Scala, right? So you can say, partition by a field, bucket by. You need to specify the number of buckets that you want to save the rows in. You can also sort it. So again, if you tend to do a lot of sorting of data, you can save it pre-sorted. So the one thing to keep in mind with partitioning and bucketing is that the way this works is that each task will write the data for each partition and bucket that it has in the data that it's processing. So if you have data randomly distributed across your data frame, you could end up with small files again. So how do you avoid that? You could use coalesce. The one thing that you have to be careful of with coalesce is that it reduces parallelization without causing a shuffle. So in some cases, that's fine, but if you have a very large job, you may need to keep that high level of parallelization so that you can run your query in a decent amount of time. So what you could do is do a repartition. It will incur a shuffle, but it helps make sure that you have nice, clean files when you write them out. So basically, this is what it would look like. All I did here is I added a simple repartition here before I write. And now when I would look at the output path here, I would see, in this case, because I'm bucketing by 10, I would see 10 nice, clean files under each partition folder. Now, one thing that can happen is your partitions might be too big, all right? And that's also something that you need to be careful of. With Spark 2.2, they added a setting called max records per file. And so this lets you control how many records you want written out in each of the files. So internally, what happens is Spark is just keeping track. Each task is keeping track of how many records it wrote. And once it reaches the limit, it closes that file and starts a new file. Okay? So this is a good way to make sure that you're not trying to write files that are too big in size. Now, you have to understand that this is happening at the task level, which means it's not parallelized. If you do need to parallelize it, if you want to control how many partitions are getting written out, you can simply repartition with some additional key. And that, again, just helps redistribute the data more evenly, and then you can control the number of files that are getting written out. All right, then another common question. How can I optimize my query? This is kind of like a loaded question because it could, you could spend a week covering different topics on this. And when I do get this kind of question from some users, the first thing I ask for is the query plan. And this is actually a small one. I've got like an ultra-wide 4K screen at home, and I have some customers that I can't even fit the query plan on that. So, okay, you tell me what's the problem here? Well, there could be a number of problems here. So here are a few. One thing that tends to trip people up a lot, and actually when I first started at Databricks and I got to meet Michael Armbrust, I kind of put him on the spot. I think he probably didn't expect that I had been using Spark for a while, and this is something that I had been fighting with for a long time. And so I immediately said, what's going on with the Spark SQL Shuffle partitions? Why is it static? There's this default setting of 200, and if you're not familiar with it, basically, this is the parallelization that Spark uses when you're running DataFrame queries. Okay, it's this default setting of 200, so it's probably big enough for most use cases, and small enough. It's like the sweet spot, right? And it's used anytime you do any aggregation, group by, repartition, join, window operation, et cetera, right? Anytime it does distribution of data, it uses the Spark SQL Shuffle partition setting. But in some cases, it may be way too big, right? If you're doing a lot of filtering, you're filtering down your data, quite a bit. You're doing, you're joining with maybe smaller lookup tables. 200 may be too big. In other cases, it may be too small. I've worked with some customers that we've had to up this significantly because they're working on such a large data set. So you can override it, but unfortunately, it's a static setting. So it applies to your whole query. So looking at this, in red are all the areas that I'm doing a shuffle. So this 200 setting, or whatever I override it to, is getting applied in all these places. Now, in some places, 200 may be good. In other places, it may be, again, way overboard, or it may just not be enough. So unfortunately, right now, it is something that you do have to kind of tweak. It's based on, you probably want to base it on your biggest query, the biggest part of your query. Now, another option is called adaptive execution. This is something that was introduced in Spark 2.0. I'm sorry, I'm going to go really quick here because I think I'm running out of time. But this is something that was introduced in Spark 2.0. And what it does is it dynamically sets the shuffle partitions based on your data volume. So it's obviously default to false. There's also another setting for defining how big you want the shuffle partitions. It defaults to 64 megs, so you can tweak that based on your use case. Now, keep in mind, this is still in development, and I've linked to the Spark Jira here, so you can see the progress of the job. But in some cases, I've seen it actually help out with very long-running DataFrame queries that have a lot of different data sizes, data volumes, or maybe working on a lot of different tables. So your mileage may vary, but it's definitely something worth looking into. Unions is also something that I've had trouble with a few times with different customers. It's important to understand how unions work within Spark. Okay, so let's say you're unioning the same data frame, right? So you did spark.read.load, you get a data frame, and for whatever reason, you need to union that data frame with itself. Okay. Then you run some sort of transformation and finally run an action. Now, the way this is going to run is Spark will actually parallelize the union, which means it's going to read the same data frame twice. Or if you union it 3 times, it's going to read it 3 times. Okay? And that's just the nature of Spark, because it sees, OK, I've got all these parallel tasks I can run. I've got so many cores on my cluster, and I'm going to run them. So clearly, reading the same data multiple times is really not that efficient. Now, I want to be clear. There's obviously a lot of legitimate use cases for using unions, but there might be some alternatives. Like some cases where I've seen people use unions is where they're trying to basically do, maybe have different versions of a row, right? They have the same data frame, and maybe they're adding additional columns, but they want different versions of the row. What you can do instead is use the explode function, which lets you essentially duplicate rows based on the return value of the explode function. So you can explode an array, and it'll add each value of that array to a new copy of the row. So you do that with one data frame in one operation versus duplicating the data frame reads. The other thing you could do is you could persist the root data frame before you do the union. Now, obviously, this depends on your data volume, your cluster size, because you're going to have to cache that data frame, right? So you could use either the local disk or in-memory, persist it, so it'll read it once, and then the union will happen from the cache. So in this case, this query has 3 unions. And if now that I've highlighted it, you can see it's running the same exact query 4 times because I did it on a union of a data frame. Okay, so I unioned the same data frame 3 times, which resulted in this running 4 different times. Okay. All right, one other thing I mentioned earlier was CostBased Optimizer. So this, again, is something new in Spark 2.2. This lets you collect and use per column statistics for query planning. So by default, Spark uses file size. So it uses file size to decide whether it can broadcast a table. But with CostBased Optimizer, it can actually completely rewrite the query plan based on these statistics that we collect. So again, this is something that requires a data source table because we're collecting additional metadata. So by now, hopefully you've seen a theme here that data source tables really do provide a lot of additional capabilities for you. We have a really excellent article on the Databricks website covering the CostBased Optimizer in more detail. But just to summarize, here's how you use it. So again, you have a data source table, whether it's unmanaged or managed, doesn't matter. There's 2 types of statistics you can do. One is at the table level, so that's just getting number of rows and size. And then the other one is you can do column level statistics, and you can actually select specifically which columns you want to get statistics on. Okay? And so again, this could be based on your query patterns. So you may not need to do it across the whole data set. If you have extremely wide tables, you can just do it on the columns that you typically filter on or do operations on. So this is something I pulled out of the article, so you can read more detail on it later. But basically, this is actually based on the TPCDS query number 25. So this is how the query plan would look like without the CostBased Optimizer. So it's doing a series of 7 joins, and the way it does out of the box is basically this tree-based structure here. So if you look at the bottom, it's joining 2.9 billion rows with 288 million rows, and then 199 million rows with 1.4 billion rows, and so on and so forth, right? Now, if we apply the CostBased Optimizer to that, so we've collected the statistics, this is actually how it ends up. So it actually reduced the shuffle size by 90%, right? So that's less, disk I/O that it's using. And it sped up the query by 3.4 times. And you can see it completely rearranged how the query is running based on those statistics that it gathered. Now, another feature that this is actually specifically in Databricks is called data skipping index. So here what we do is we create an index over data source tables. Again, it requires data source tables. And it lets us capture an index over each of the files in each of the partitions. so that when we do filtering on a data set, we can actually completely skip files that don't have any of those values that you're filtering on. And it's completely opt-in. You know, you just run this command here at the bottom to add it to your data source. I've linked to the documentation on our public documentation site so you can see some more examples. And here is a simple query that I ran on the data set I was using earlier. So doing a filter on the customer primary key, doing simple, between 1 and 10. Without the data skipping index, it took about 18 seconds. And with the data skipping index, it went down to about 3 seconds. And again, especially working on S3, this really sped things up because it's completely skipping files. It's not loading them, and it's not having to apply any filtering within Spark. It completely avoided loading those files. So if you want to try that out, and a bunch of other features that we've been adding to Databricks Runtime, I definitely encourage you to try Databricks. You can go to databricks.com and play around with this in the Community Edition. And I also wanted to plug the new book coming out by Bill Chambers, who's one of our PMs at Databricks, and Matei. We have a preview available that you can download the ebook, and it should be out October? Cool. All right. So sorry for going real quickly there at the end, but thank you. This is my info if you need to get a hold of me.
Thank you.